In this video, we're going to work an eigenvalue, eigenvector problem when we have a complex eigenvalues to work with. I think this is video number 19. In the earlier videos, 16 and 17, we had worked out eigenvalue, eigenvector problems, but we did not have complex eigenvalues to deal with. So we'll do that in this video. Before we do, let's just review in general what happens when we encounter an eigenvalue, eigenvector type situation. We have a matrix that some vector is going to be multiplied by, and once we do the whole row column multiplication procedure, all we end up with is just some number times the eigenvector. And as we'll see in this video, this can be a complex number. Now we can subtract from this side of the equation, bring this over here, and we realize the eigenvector can be multiplied by an identity matrix, and that doesn't change it. Let's just take an example where it just has two components, x1 and x2. So this would be the identity matrix. Do the multiplication, and we still have x1 and x2, which of course are the original components of the eigenvector. So up here we can multiply the eigenvector by the identity matrix I, which we have right here. Then we can factor the eigenvector out and have this expression. And we're going to write this now in component form, but we'll just have a 2-by-2 example in components. So we'll have lambda 1 times this, which will be lambda 1 here, lambda 1 here. So we will have this expression. Here's our matrix in component form. Here's lambda 1 times I, and we do the subtraction. So we have this subtracted off from this component, and this subtracted off from this component, leaving us with this equation. Now, if this is to have a non-trivial solution, our matrix here must be singular. So this determinant has to be equal to 0. And of course, we take the determinant, set it equal to 0. That's how we determine what lambda is, the eigenvalues. Once we know these specific numbers, we can put them into this equation and then solve for the components of the eigenvector and then determine what the eigenvector is. That's what we did in videos number 16 and number 17. But we had real numbers here for the eigenvalues. What happens if we have complex values? That's what we want to take a look at in this video. So here is our matrix. We want to know what are its eigenvalues and eigenvectors. So we have it like this. We know the determinant has to be 0. So we have this times this, 3 minus lambda, times minus 5 minus lambda. This times this minus negative 20. Minus negative 20 is plus 20. We have minus 5 minus lambda. Let's factor out a negative 1. And then this will be positive, plus 5 plus lambda. So we'll multiply these two expressions, remembering that we have a minus sign out here. And this will give us 15 plus 3 lambda minus 5 lambda minus lambda squared plus 20, and the determinant has to be equal to 0. So let's see, we have here plus lambda squared we have 3 lambda minus 5 lambda, that's minus 2 lambda, times negative, that makes that plus 2 lambda. Then here we have minus 15 plus 20, that's plus 5 equals 0. And we can't factor this out, so we'll have to use the quadratic formula to do this. So we have lambda equals minus b, that would be minus 2, plus and minus the square root of b squared, that would be 4, minus 4 times a, the coefficient of that, that's 1, times c, that's 20. So you have minus 20, minus 4ac. A is the coefficient of that, which is 1. C is this, so we have minus 4 times 5, minus 20 here, divided by 2a. So that's just divided by 2. So here we have minus 16, so this is minus 2 plus or minus the square root of minus 16, that is 4 times I, divided by 2, or this will be minus 1 plus or minus 2I. Now notice what's happening here. We have a complex value for the eigenvalue. Actually, we have 2 of them. Not only do we have 2 of them, but they are complex conjugates of each other. We have a real number plus a complex number, or a real number minus the same complex number. So whenever we have eigenvalues that are going to be complex, they're going to occur, because of our quadratic formula here, they're going to occur as complex conjugates of one another. So we'll have lambda 1 equals minus 1 plus 2I, and lambda 2, that equals minus 1 minus 2I. So these are complex conjugates of each other. And that will happen, oops, let's get this in better view. Lambda 1 is minus 1 plus 2I, lambda 2 is minus 1 minus 2I. Lambda 1 and lambda 2 are complex conjugates of each other. Whenever we encounter a complex value for our eigenvalue, it will have to occur as complex conjugates because of the way the quadratic formula is set up. This is the part here that gives us the complex part, and we have some real number plus or minus that. The reason why we have a real number here, though, is because our matrix itself has real components. So a matrix has real components. Its eigenvalues can be complex. When that happens, they will occur as complex conjugates of one another. Okay, let's go ahead then, and we want to determine the corresponding eigenvectors for these 2 eigenvalues. So let's erase the board and make some room, and we'll proceed with that. So lambda 1 is minus 1 plus 2I. Let's start with that one first. So we had this, and the lambda we're going to use, lambda 1, is minus 1 plus 2I. So I have here 3 minus lambda. So we have 3 minus negative 1, that's 4, minus 2i. Then here we have minus 5. Here we have 4. And here we have minus 5 minus lambda, minus 5 minus negative 1, that's minus 5 plus positive 1, that's negative 4, and we have minus 2i. So we plug in the specific values for lambda. Remember how this works now. This times the components, we'll have 2 of them. These are the components now of our eigenvector corresponding to that eigenvalue, and those have to be equal to 0. And the reason why it's like that is based upon what we did previously. Remember, we had this equation. This is where we're at right now, except we plugged in specific values for lambda, and we have the components now of the eigenvector that equals 0. The reason why it equals 0 is because of what we did previously. So we want to solve this now for x1 and x2. So let's look at what we have. Here then we'll write this as an augmented matrix. We have 4 minus 2i. We have minus 5. 4 minus 4 minus 2i, and writing this as an augmented matrix. And here we have 0, 0. Okay, we can divide this first row by 2, and that will give us 2 minus I, and this will be a 2 here. So dividing the first row by 2 to make it a little bit simpler, we have 2, just minus I, and this is 2. Now, what we want to do is we're going to use Gaussian elimination. We don't only have to do it once, but what we want to do then is we want to multiply this by some number so that gives us plus 5. So that when we say, okay, we're going to multiply this row by some number so that this is plus 5, so when we add up to here, that comes out to be 0, so we can knock this out. So what number do we have to multiply this thing by to get a plus 5? So let's see, we have 2 minus I times some number we want to equal plus 5. So the number that we're seeking here, n, equals 5 divided by 2 minus I. So we can go ahead and do our rationalization like this. So we can determine what n is. And here then, down here in the bottom, we have 2 times 2 is 4. The cross terms cancel out. I squared is negative 1 times negative number here. We have here 4. 2 times 2 is 4. Minus 2i plus 2i, that's 0. Then we have minus I squared. That's 4 minus negative 1. So the denominator is 5. So this equals 5 divided by 5 times 2 plus I. So the number we're seeking is 2 plus I. So we're going to multiply this row here by 2 plus I and add it to this row so you can make this 0 and solve our equation here, solve our augmented matrix. So let's go ahead and do that. So we're multiplying this row by 2 plus I. And that is just barely visible. Let's write it on this side. We're multiplying the row by 2 plus I. So we do that, and what happens? Here we have 4, we just did this, minus 2i plus 2i, that's 0, minus I squared, that's plus 5. That's what we want it to be. Add it to there, we have 0. So our new matrix will look like this. Add, this is 0. We multiply this by 2 plus I. We're going to have 4 plus 2i. 2 times 2 is 4 plus 2i. We get a bonus that knocks out this one too. So our augmented matrix is like this. And in the previous videos, we explained how lead variables and free variables work. This, of course, is the column for x1. This is what the column for x2. So that's our lead variable. This is the free variable. So we have that 2 minus I times x1 equals, well, let's just write it out. 2 minus this plus 2x2 has to equal 0. And again, this is our lead variable. We explained lead variables and free variables back in videos 4, 5, and 6. So what do we have here? We have x1 equals minus 2 divided by 2 minus I. And we can rationalize times x2. Just putting this over on this side of the equation. Now we can rationalize this. Multiply top and bottom by 2 plus I. Times x2. So we do that. Remember, this comes out being equal to 5, that denominator there. So what we have is x1 equals minus 2 divided by 5 minus 2/5 times 2 plus I times x2. And remember, x2 is the free variable. It can take on any value whatsoever. But let's go up to here. What is x1? It is minus 4/5 minus 2i times x2. So we're going to have to make some room to write all this in. So let's erase this stuff now. Sorry if this takes long, but the procedures can be rather tedious. But if we follow the steps, we should be all right. Okay, x1 equals 2 plus I times minus 2/5 times x2. So that's minus 4/5 minus 2i/5. So we have x1 is minus 4/5 minus 2/5 I times x2, our free variable. And x2 is just x2. So this is this. We can write this differently now, of course, by factoring out the free variable x2. So if we do that, this will equal x2 times, here we have minus 4/5 minus 2/5 I, and down here just 1. So that's our eigenvector. x2 is our free variable, meaning it can take on any value whatsoever. We can take the simplest value when x2 equals just 1. So we do that, and we have our corresponding eigenvector, x1. Here are its two components. Again, this is a free variable. It can take on any number whatsoever, so we can just have it be 1. So for lambda 1, which equals minus 1 plus 2i, the corresponding eigenvector is this, minus 4/5 minus 2/5 I, 1. There's the complex eigenvalue. There is its corresponding complex eigenvector. And if you weren't clear as to why x2 was the free variable, please go back and look in videos 4, 5, and 6 when we first discussed free variables and lead variables, and also in videos 16 and 17 when once again we used the concepts of free variables and lead variables when we were solving eigenvalue, eigenvector problems. But okay, we have part of our answer for lambda 1. Now lambda 2 is its complex conjugate, minus 1 minus 2y. Will our second eigenvector, will that just simply be a complex conjugate of this eigenvector? That will determine in the next video. This one is getting a little bit long, so come back for the second half of the video. We're going to consider this eigenvalue now and its corresponding eigenvector, and we'll ask the question, does the eigenvalue that we get for here, is it the complex conjugate of this eigenvector? After all, these eigenvalues here are complex conjugates of one another. Come back, join us in the second part of the video, and we'll finish off this problem.